Hello, and we are getting ready to do a walkthrough of an economic systems model view of addiction. And with a little luck, I will begin with a successful screen share of a Google presentation. And I am working on pulling that over into your screen, and hopefully it will come together very well here. So this is an updated version of a model that many of you may have seen in class already before last year in systems, and I've tried to update it to make it more intelligible, and I will also be sending out slides and other things with the script so that people can follow along at their own pace. So let's begin with the users, here identified as opiate users. The nature of the addiction is not the most important point. As long as the drug is illegal to possess, sell, and distribute. Opiates are named only because of the current saliency of the issue and because I've added a submodel a little bit later that looks at the phenomena of legal prescription pill use leading to an increase in the population of street addicts. A reminder about the visual vernacular used by Stella, and this is using Stella Architect trial version just to update the model that I had made in a previous version of Stella that I own, but that was inconvenient to use on my computer, so I've used a more up-to-date version just to showcase that. It's Stella Architect. So the rectangle is a stock, something which can be counted or quantified as going up or down in quantity. The arrow is a flow, which is a rate of change for the stock. An arrow going into a stock is an inflow, which represents a rate increasing the stock. Going out is an outflow and represents a rate decreasing the stock. Stella is also a mathematical modeling tool as well and works mathematically by calculating all of the rates of change and all of those interconnections of the model per a chosen time interval, and then models the behavior over time. We could, for instance, set the new user rate at 5 new users per day, and then run this simple model with a 1-day time interval for 1 year. If the stock was set to start at 0 at the end of the 365-day simulation, we would have a stock value of 1,825, representing users who began using. Of course, the real world has a constant churn of people beginning to use, continuing to use, and stopping for a variety of reasons. This is visually modeled by 3 different outflows, each of which offsets the rate of growth. By separating them, each of the flow rates could be adjusted to data. For instance, if the death rate was 1 per week, that would be 1/7 per day. The cessation rate, 1 per day, and the incarceration or removal to treatment rate set at 6 per week, which is 6/7 per day, then the cumulative effect over time would be 2 fewer per day. The stock would then grow each day by the difference between the growth rate and the combined cessation rate, which in this example nets at 3. Remember, this is an economic view of the system, so the elements of the model reflect the users as customers. And because we are thinking of the users as customers, let's begin building the economic system around them. Here we see the stock for the street price of the drug. Then this image is the beginning of a rudimentary supply and demand system. The price reflects the relative weight between the impact of demand on the system, which drives up the price, and supply, which lowers it. Here we've added another flow. This flow represents the effect of dealers choosing to discount and/or flood the market in order to gain new customers. In a model with equations, this could be triggered by other changes in the system, set as a random function, or set to occur periodically. The equation allows for a blend of mathematical relationships and logical functions, so you can create if-then and other kinds of conditions to trigger the discounting behavior. This addition to the model represents an economic theory that a high street price is a barrier to new users and that discounting can capture a slice of non-users and turn them into users. This would be a place in the model where we could add another subset that is opiate specific, users who have become dependent on prescription opiates. Let's look at that, even though I'm not including it in the final model. So here we have a simple model describing the mechanism by which the legal use of prescription opiates leads to an increase in users dependent on street supply of illegal opiates. This submodel shows how interventions can lead to unintended consequences. And I'm going to pause here for a second, have a cup of coffee while you look at the image, just for 2 seconds. Okay, so on this image, the starting point for our tour in the top left is patients being prescribed pills. Some percentage of those become addicted, and that shows up as you go through the prescription opiate addicts, the percent who become addicted, that's the converter circle there, and eventually use up their supply. So you can see that their average daily use correlates to their use, their supply rate, and all of those other parts of this little submodel. But basically, eventually, users who have become addicted without legal access to their pills will eventually use up their supply. So you have some known, or predictable percentage becoming addicted, using up all of the pills that they've been prescribed, and then becoming captured by this stock that we call addicted users without legal access to pills. And the bigger that number is, the more pressure there is on the street supply of pills, and the higher the street price goes. Law enforcement actions to restrict supply also increase the price. And then we have here in the top right, doctor behavioral shifts may reduce the number who become addicted through the use of shorter duration scripts and better coaching, but that also lowers the average pill inventory, which potentially lowers the diversion rate or theft and or selling, because there are fewer excess pills floating around. The lower the diversion rate is, it also reduces street supply, which puts upward pressure on prices. So what you have is a simple model that shows that the more people there are of prescription drugs, and the more strict we are about controlling inventories, limiting their access, increased law enforcement, all of those factors means that for the slice of people who become addicted through legal prescriptions initially, but who eventually run out of access, those people are in a system where the price is increasingly expensive on the street for the drug that they're addicted to, and they become then very vulnerable to a phenomena that we described in the original model, which is the discounting. And here you see that while they may not want to switch, these addicted users of expensive prescription opiates are easy marks for substitution of cheaper street opiates. And price is a barrier that can be removed by dealers looking to expand their customer base. The part of the model we just looked at for street price has an outflow called supply factor, which is actually really connected to the function street inventory. The supply factor flow serves to link the model logic of the inventory, street inventory, to the price. And when street inventory is high relative to demand, prices will fall. And when inventory is low relative to demand, price will rise. So the model spreads out that basic supply-demand dynamic over two different stocks to better illustrate other system effects on the supply-demand system, and we'll get to some of those. So this view shows two different mechanisms by which street inventory can be diminished, and the inflow rate, which can go up or down in response to demand. The confiscation rate reflects law enforcement activity. The consumption rate could be designed to change in response to other factors. For instance, if research showed consumption per user changing predictably over time, either because of the nature of opiate addiction patterns or in response to some external intervention, we could model that if we wanted to in a more complex mathematical model. This slide shows that we have made the connection between street inventory stock level and the street stock price. Stock here, unfortunately, means in colloquial English also can mean inventory, but in this case I'm referring to the stock element of the Stella model. So we're showing visually the link described a couple slides before of this relationship between supply and demand and how the model splits them into two stocks. the aspects into two stocks to highlight other aspects of the system and their effects. The arrow is pointing to the red or pink, depending on your screen, arrow, which means that there's a logical and mathematical connection between those two. So now let's shift our attention to how the street inventory is moved, which is dealers. Here we have three factors representing changes in the number of dealers. One is a generic inflow rate, which will capture shifts in factors which tend to increase the number of dealers. We will highlight two of those shortly. For outflows, we focus on two aspects of the decline in the number of dealers: people who choose to leave the business and people who are arrested. There are others not modeled, such as murders over territory, dealers who are also users and overdose, etc. This slide shows that there is a connection between the number of dealers and street inventory. This is logical, as someone has to move the product from production all the way to the end user. In an illegal system, this is a labor-intensive part of the business. Supply will be constrained or tied in some way to the availability of dealers to move it. So what drives the growth of new dealers? One factor is clearly the profitability of the activity. Anecdotes here. I used to have an employee who was a child of poor immigrants. He was recruited into a gang at 13. And by the time he worked for me as a young 20-year-old, 22, 23, somewhere in that range, he was clearly dealing. He worked as a cook, but had a fancy car, fancy clothes, and fancy technology. The lure of the wealth had helped him move from a grunt in the system to a local player. And I mean player in the sense of, he was a fairly significant dealer within the local market. The good news is he has now left the life, is married with kids in a highly successful business. But certainly at the time, he was very cognizant, and I've talked with him about this quite openly, about how the money was a powerful attractor for him. I also had another employee who was able to make $700 a week profit selling pot. He made one trip to his dealer, sold all what he wanted for himself and his friends, basically before he even got home, and took home a net of $700 a week. He was 19. He also left the life, which is why I was able to get sort of the story of the economics of it from him eventually, after 2 years of me working him over about what I knew he was doing, but he wasn't willing to admit until he left the life. Came into my office one day and said, so I sold my scale. And that was the entry point into us having a more honest conversation about the economic model that he had been participating in. So these stories highlight how profit is one aspect of what can draw people into becoming dealers. We're going to bounce here. This image shows two dotted line stocks. These are called ghosts in Stella, and they are simply ways of bringing the stock value into a different part of the model without drawing long arrows across the model. We've discussed profit, which as you can see on the left, but you can see that I've also added a conversion of users who become dealers. This is a reflection of the fact that becoming a part of the system is a rational way for addicts to ensure access to supply, and so predictably some percentage will do so, especially as the street price increases, which is why the street price stock is ghosted into this section of the model. So returning back to the profitability aspect of the model, we need to build out some detail of what drives profitability in the system. So here you have the unghosted stock, which shows a very simple calculation. And let me comment parenthetically, you'll see that when you ghost one part of this, the stock over to another part of the system, it leaves intact all of the other pieces around the stock, but it doesn't carry those with them. So again, you're using that ghost function to carry the value of the stock over it, or a converter or something else, into another part of the system for mathematical and logical purposes, but it doesn't carry all of the other parts of it with it, even though those are still connected at the mathematical and logical level underneath the visual layer. So here we have a very simple calculation. Profit, in this case, is the sales price input minus the costs. So some of the costs which affect the cost rate are separated out in these different converter circles and should be relatively self-explanatory as to sort of typical costs of production or sale and sort of general economic activity. So materials, capital costs, labor, security, transportation, etc. This image highlights that the street price is linked to the other part of the model where we explored the street price dynamic. you could, sorry, the street price rate. So you could link the stock directly or use an arrow, as I have here, to show the relationship and handle the details within the model's equations if you were using the mathematical model. I thought it would be easier to sort of see the connection with the arrows. That's why I chose that method of doing it. But you can make these mathematically equivalent to each other if you needed to. So it's important to see that all of these different parts of the system are in constant relationship to each other, and that shifts in one area affect other areas as well. So this image, there's actually nothing new about this stock. This isn't another type of stock other than when I took the screenshot while I was selecting it for, it had been selected for editing, so it was trying to ask me if it wanted to be resized. I apologize. But we're moving now and shifting our attention a bit to extend out the ramifications of profit on the system. So production of new drug supply is correlated to profit. If no one is making money in the system, then production will dry up. If demand is growing, profits are high. That will invent new production. Others, people will jump in. I said invent, I meant incent. I apologize. New production. This dynamic response to other aspects of the system is a good reason to include some abstraction of the production system in the overall model. So here we have the inflow, simply a way of capturing the combined effect of some of the factors which would boost production, most obviously profits. The outflows represent different ways that production diminishes. Interdiction is technically an intervention into the shipping process, but it could also affect the materials required to produce capacity. Eradication and arrests are self-explanatory. So this image shows that arresting producers is another way to reduce profitability by driving up the cost to produce. And then this arrow shows that the profit is a driver of new production because it creates the incentive to produce more. So here we have a slide that shows another place where the supply chain can be disrupted to affect price. If supply is reduced by arrests of producers, which we've now ghosted into this part of the model, then the supply rate declines and price goes up. Remember that if price goes up, profit may also go up. So scarcity can be extremely profitable for the people who have the supply if demand is not curtailed either by price or by the nature of the eviction, is not curtailed usually by price going up sky high, but the nature of addiction is such that that usually doesn't happen. So this image puts together all of the aspects we have talked through, and I encourage you to pause the video and review the slide just to get a sense of the overall system. In fact, I will pause within the recording itself briefly just to make sure that that is easier for you to do. So now I'm going to move to several different abstracted views of the same underlying model. And in this case, what I've done is I've tried to highlight different aspects of the system and imagine sort of what is visible to different actors within the system. How do they tend to see the system, or at least how do they mostly experience the system? So the first place I'll start is with users. So this imagines what the system looks like to the user. For them, the system is often about their use and its risks, their dealers, and the ramifications of the cost of drugs. So you can see that we've kept in overdoses, incarceration, removal into treatment, or other ways that they sort of get out of using, their ability to stop, what the street price is or what it is if it's being discounted for some reason. I might mention here that street inventory is only noticeable if it approaches zero. Really, the mechanism of supply and demand is not so terribly important to them. It's price and availability. If availability is not zero, then it's price that matters. And then in terms of dealers, whether the dealers are around, if their dealer's arrested or gets out of the business, then they've got to find another supplier. So again, this is trying to highlight the way that they would likely see the system. So we could also model user behaviors in response to these factors, but for now, just look at this as the way the system is visible to one set of actors within it. And we'll look at a couple of the other actors' views next and just to be clear, this is not to argue that users are not able to study the system and understand it, but rather that the primary way that they experience the system, or the primary ways that they experience the system, are mediated by the elements in the image. This view is a more complex view, and it is intended to highlight the parts of the system that are most salient for law enforcement, as these are the areas where they are most active. If you look back at the whole model, you will see that I've used orange to code the areas of intervention used by law enforcement to change the system. Many of these have unintended consequences, as we have seen and explored how limits on supply drives price up and drives profitability up without lowering demand. This spurs new entrants into the market as dealers and producers and puts pressure on addicts to become active dealers as well, because the price pressure creates problems for them. This is also the point at which the success of law enforcement in driving up the street price also creates an incentive for users to steal in order to have the money to buy the street drugs. I haven't highlighted that in the model, but it stands to reason that unless demand is curtailed, all of the activities highlighted above have a negative effect on theft rates. This is a bit like a balloon being squeezed, where the balloon represents criminal activity, and putting pressure on all of the highlighted areas, where I pointed to with the arrows, creates new incentives for theft and criminal activity elsewhere, such as production and dealing, all driven by the price effect on the system as a whole. It is also true that law enforcement, if it just focuses on its levers, may not see the whole system very well. For the human service system, the areas in the model where policy interventions are pursued are more people-specific and have been highlighted by the color green. In this image, and again, both of these color highlights go back all the way throughout the model design. So if you look at the whole system, you can see the different parts of the system where the color coding kind of gives you a lens to which part people are primarily active in or primarily is visible to them. In this image, I've actually added some descriptive converter circles and arrows that are not in the underlying master model to help show what the implied interventions might look like. And these interventions will mostly affect the demand for drugs, which means that they also lower the incentives, which fuel the growth of the other more negative parts of the system, such as production, dealing, etc. Not completely or universally, as some of these interventions are actually harm reduction strategies. So Narcan saves lives, which is obviously great, but it does not by itself reduce usage, because saving the life of an addict doesn't make them less of an addict unless they are able to stop using. As with other views of the system, human service actors can see more than just these activities, but it is also true that their day-to-day view of the system is largely this subset of it. The final system view is that of the dealers, in this case the high-level ones who can see the whole system. And I've added this because it helps set up the final slide, which is an abstracted view of the same image, where drug-specific language has been replaced by generic business language in the next slide, and it becomes easier to see how this system truly is a small economy with its own internal rules and structures. So here I'll switch to the final slide, where I've now abstracted those elements, and you can see customers and sales price and market penetration, production capacity, profitability, scaling up, cost of goods sold, departure rate, competitor activity, discounting, and sales. So you have here this abstracted view of the previous slide of the system, which in many ways we could plug in any number of different markets and see that the basic structure of the system mirrors many other economic systems. And again, from the perspective, I'll go back to this, from the perspective of sort of the high-level dealer, they can see the business as a whole and can see the ways in which the other actors in the system are affecting their business one way or the other. So this is the end of the presentation, and gives you just another angle in to understand and evaluate the addiction system, and hopefully by having a chance to preview the slides and preview the model as a whole, we'll be able to talk about it a little bit more in class and address any questions or any interesting thoughts that people have in response. Thank you.